The following program is brought to you by Caltech.
So our next speaker is Dr. James Cutler, who's an assistant professor in aerospace engineering at the University of Michigan and is director of the Michigan Exploration Lab. He is co-eye of two CubeSat missions funded by the NSF, the Radio Aura Explorer, REX, and the CubeSat investigating atmospheric density response to extreme driving, CADRE. He's also co-PI on two technology demonstrations for the JPL and a number of other CubeSats, including MCubed. I will hand over to Jamie straight away.
Thanks, Michael. It's a pleasure to be here. Thank you for the invitation. It's great to put names, faces to names and things like that. Thank you for the talk earlier on the science side. I'm on the engineering side, so it's always great to see a scientist who is just as excited about these platforms as I am. They tend to be a little crazy, and that's even better. Also, the light bulb comment that was made during the first talk, if you do a search on light bulbs and space station, you will find an interesting trade study that's going on where the light bulbs were expiring on the space station. They didn't have replacements. So they were funding a multi-year study to understand how LED light bulbs perform on space. So you can answer that question quantitatively. So let me give you a little background. Back in 1996, I was a grad student at Stanford, and I wanted to get involved in building things again. I was tired of theory, and I wanted to get my hands dirty. I wish I'd delayed this by a couple of years because Larry Page's office was just down the hall from mine. And if I'd gotten hooked up with him a little bit earlier, then maybe we could be funding these missions. That said, we built a spacecraft. We built a couple spacecraft out of Stanford. And over on the left-hand side is the Opal satellite. You can see an open door there in the middle. And what was originally supposed to go in here were free-flying magnetometers from JPL. So in many ways, the desire of flying distributed sensors came out of JPL. Unfortunately, funding was cut, and our mission continued without JPL involvement. However, that 4-inch dimension that was mentioned with respect to CubeSats came out of this bay because we had 1 by 3 by 4-inch picosatellites. That 4-inch expanded into the Beanie Baby box, which became the CubeSat. So we launched this spacecraft. We had a variety of picosatellites. One of the things that came out of that effort was the fact that our picosatellite providers could deliver the spacecraft well after we had delivered the mothership. So it's then that the community realized the launch vehicle interface was key. With that standardized, with that flight-qualified launch vehicle interface, you could launch a variety of new things. So from this came the CubeSat mentality, came the P-pod interface, and really it was about the launch vehicle interface. Yes, it's constraining. Yes, you have to fit in the box, but yes, we are launching. And that's an exciting, exciting opportunity. We did build our satellites in more or less the garage, and we took a lot of shortcuts. Not shortcuts, actually we did take cuts. So Andrew mentioned using a saw. So you can see the spacecraft here. There's a magnetometer. That magnetometer used to extend well up, probably 2 feet above the spacecraft. When we were mounted onto the rockets, that was going to be outside the fairing. That was not an option, so we cut it off. And we flew our magnetometer. So the saw work became very handy. Also, the integration is fundamentally a challenge. When you buy parts from a variety of different places, putting them together can result in wonder, can result in sparks, can result in smoke. And when we took our spacecraft outside and turned it on, we lost all of our telemetry. So we had no voltages, we had no currents, we were basically blind with respect to our spacecraft. So we carried the spacecraft back inside, turned it on, and it worked. Took it back outside, turned it on, and it failed. So can anybody figure out the difference between those two environments?
Thermal. Sunlight.
Not thermal.
Sunlight.
Sunlight. Okay. So what had happened is our panels were illuminated. Those panels were generating voltages, which were going into analog to digital converters, which were powered off because of the separation switch system. However, the voltage inputs were not cut off, severed from the system. So there was power leaking into our analog to digital converters. So every time we powered up in the sun, we lost all of our telemetry. So we called up Major Buckley and said, Major Buckley, are we going to be launching in the shade or in the sun? He checked his engineer and said, you'll be launching in the shade. And we said, thank you, sir. And that's how we launched. Because at that point, it was too late to integrate. We were on this very, very rapid cycle. And fortunately, we did launch in the shade. We did deploy our spacecraft, and things worked phenomenally well. This is the first launch of the Minotaur rocket. You can see it heading off over LA over here. It was a sun-synchronous terminator orbit, so we were riding the dawn-dusk line the entire time. This is actually the second launch, but it's in the daytime, and I wanted to point out various features of this rocket. So speaking of thermal issues, the transmitters on the rocket were overheating, and as they overheated, they needed to cool them down. So they needed to get a very cold source of air up to the rocket to cool down these transmitters. Can anybody recognize the color of this cooling system? It's orange. Does anybody know of any circular, cylindrical, orange cooling devices? Does anybody watch football? Gatorade coolers, okay? So this is a Gatorade cooler attached to the rocket. So when people talk about the professionalism of how certain things are done, this thing is covered in duct tape, this rocket. They don't call it duct tape, they call it rocket tape. And there are Gatorade coolers on it. So there's very much this fly by the seat of your pants, figure out things as you go to build these quick, rapid missions. And that's how they get done. This is fascinating data. I won't dive into the details of it, but this is 3 days worth of data. Day 1, day 2, day 3. This is temperature data. I hate temperature issues. Yet they keep cropping up. For the first day, great. Our internal temperature is running about 25 degrees Celsius. Perfect, just where we wanted. Something happens. Our bottom face faces the sun. Our batteries reach almost 100 degrees Celsius. So has anybody taken a battery up to 100 C before? Does anybody know what happens when you do that? Boom, they blow up, okay? So fortunately, our batteries were encased in epoxy inside a aluminum brick. And we also lost communication with the spacecraft at this time. We were competing with JPL to use the 50-meter dish back behind Stanford. You guys were going after one of your spacecraft on Mars that was having communication issues. We were going after one of our spacecraft that was having communication issues. So we do a pass, you bring the feed horn down, you lower it, you swap out the hardware, bring the feed horn back up and do these contacts. It was a pretty exciting time. And we were able to fake the spacecraft out, get communication back up into it, deployed our daughter satellites, our Pico satellites, spun the spacecraft back up. And it turns out we had recontacted, we had hit another spacecraft at that time. So when we launched from the Minotaur, we came off cross track. So the spacecraft were essentially flying like this. And we hit an inflatable sphere. And you can tell by the orbit elements that we changed orbits, and it just happened to stop our turning motion. And we would have lost the spacecraft if we hadn't been able to spin it back up. That is the first spacecraft that I've had contact another satellite. Recently with our partners here at JPL, we've had a second satellite recontact another satellite, and it's physically stuck to the other spacecraft. Space is big. I've heard some big ideas on docking, and I've already done it. We've already done it, unfortunately, but it's a possibility. So you can cite us as heritage. So this is back in '96. We launched Opal in 2000. Out of that came the CubeSat standard. One of the first spacecraft CubeSats that were launched was called QuakeSat, and it flew a VLF magnetometer. And it was an interesting experience into trying to figure out how to do science with these small satellites. That's where I learned that the science world was very, very different from the engineering world. In fact, one of the spacecraft that launched there, Psi-4 from Tokyo, is still operational last time I heard. And that was from like 2001, 2002 timeframe. So it's been taking pictures for a very, very long time. But back in 2007, the National Science Foundation came together and said, hey, look, can we do anything with these CubeSats? They called together their entire science community. They called together the ionospheric community. They called together the magnetospheric community. They called together the heliospheric community as well. The ionospheric people said, yes, no problem, we can do it. The magnetospheric people said, maybe, we might be able to figure it out. The heliospheric people said, no way. Our telescopes are too big, it's impossible to pull this off. So the NSF program focused on some of the ionospheric missions at first. I'm excited to say that magnetospheric scientists are proposing various missions now. Some are being funded, and there are even heliospheric people who have missions built and tested within a few years after 2007. So NSF came along and said they offer great potential, and potential is the key word. It's not a sure thing, but there's a chance for innovation. It's also very, very important for training the next generation. Right before 2007, NASA came along and said, it's not our job to train the next generation with building small satellites in a conference at small satellites. So in many ways, NSF stepped up to the plate and said, this is important to us, and we're going to go for it. It's also very important for maintaining creativity and innovation. Experience is not always right, as we heard earlier. These students have crazy ideas, and often they work. Many times they blow up. So the constraints were huge. We heard a lot about the CubeSat constraints in general. I never realized how important millimeters were, sub-millimeters were, until I saw the CAD drawings come out of Andrew Coleman and the pumpkin work that he was doing. Every little detail counts on where things go. 10 by 10 by 30 centimeters roughly is not a lot of space. So when we got the RACS mission in September 2008, I had just left Stanford as director there, moved to Michigan, and I had an empty lab. So it's a little bit smaller than this. I had no team, but we did have this NSF mission. It's confined to the CubeSat form factor. For better or worse, we had a launch. Having a launch is great because you get the space, but it's also a driving factor on your schedule. So we played launch chicken with this rocket versus us. It was the first launch of the Minotaur 4, and odds are that it was going to delay, and fortunately it did. We were in a 650-kilometer orbit, which is fairly high, and that has deorbit issues, deorbit constraints. So we're required to deorbit within 25 years, and we had to keep our mass under 3 kilograms. The standard would have allowed us to have gone further, higher in mass, but we had to keep it light. We also had to deliver our first spacecraft in less than 12 months, and that was a challenge. RACS is what's called a university class mission. So Mike Swarthout a few years ago coined this term. And we're doing brand new novel things, but students are at the heart and the core of what we're doing. And that's both a benefit and a challenge. So it's a benefit because they're passionate. They have far more energy than I do or you do, unless you're a student. They also are very creative, but at the same time, they don't know as much as you would like them to know. So you have to give them room to explore, give them room to fail, give them room to blow things up, destroy things. And out of that will come a very, very interesting activity. So the chief scientist on this mission is Hassan Bachavan. You can see him right here. We spent quite a bit of time actually at a CubeSat workshop at Cal Poly with several pieces of white paper, going through a lot of different ideas. And that's impossible. We can't build that yet. It's too expensive. This, and this. And finally, we settled on this RACS mission. That was both doable and novel in the time frame, and I'll talk about that. I started to lose track of how many students, how many people have been involved, but we have a variety of students that have pretty much carried the weight of what we've done. So as a motivating example, this is a great picture that was taken back in 1859. A drawing, excuse me, an artist rendition. The reason why I said pictures is because last night our arrival was delayed. We turned into a red eye, and magnetic activity was really quite high. KCP was 6 as we took off, and that's a level of global magnetic activity. The auroral zone was dipping down into Canada, dipping down into Wisconsin, near Michigan, and actually as I was flying, you could see the aurora. It was a faint glow, and you can see a little bit of the structure. And I tried to take a picture, but the flash kicked back in my eyes and blinded me. So even after that, the iPhone just wasn't good enough. However, this was a monster storm that took place back in the 1800s that really affected society even back then, even though electronics weren't a fundamental part of what they were doing. Telegraph machines were operating without power. So imagine that kind of energy being dumped into our power grid. It also affects communication as well. So RACS is a fundamental science mission attempting to understand the basic physics of what's going on in the ionosphere. So one of the challenges is that we can get up into these regions with sounding rockets, but they tend to be very short-term missions, lasting on the order of minutes. And we can't do any sort of long sustained measurements. These ionospheric disturbances create anomalies. So this is a increase in plasma and electron content near the equator. Does anybody know how these measurements were made, or can guess how they were made? So, Geiger tube. These are Earth-based sensors. GPS. All right. So GPS receivers, in and of themselves, are sensitive enough to see these disturbances. That means these disturbances affect a GPS. So very simply, just like stars twinkle in the sky, the spacecraft will twinkle as well, the GPS spacecraft, and that introduces error into the GPS receivers. So being able to understand this is very important for communication as well as GPS. So the RACS mission is a novel concept of a bistatic radar system. So we take advantage of extremely high power transmitters on the ground. So this is a picture of Arecibo. We haven't used Arecibo yet. We've been using radars in Canada and in Alaska. They are installing a heater system in Arecibo, which means they can generate these ionospheric disturbances man-made, which means we're going to partner with Arecibo to go look for these when we want to. And then here's our receiver system, which is the RACS spacecraft. So if we draw it a little bit more to scale, we've got very large radar systems interacting with very, very small spacecraft. Here's sort of a pictorial of what's going on. We've got a ground radar that we partner with in Poker Flat, Alaska, near Fairbanks, and it transmits 2 megawatt pulses up into the ionosphere. These pulses interact with these plasma disturbances that are in the ionosphere, and the challenge is that they're aligned along the Earth's magnetic field. So due to the geometry, with the magnetic field coming down, essentially, the reflections head off into space. So normal radar, you transmit, and it comes right back at you. And you can have a monostatic radar where the transmitter and the receiver are the same. Bistatic means that the transmitter and the receiver are separate and allows you to give additional insight into the problem. So this radar illuminates these anomalies, and then the RACS spacecraft flies through and picks them up. Here's the Millstone radar out east on the East Coast. This dish is very similar to the Stanford one. And we plan to do some experiments with them as well. So here's a picture of the RACS-1 spacecraft on the left-hand side. This is a 3U satellite, so 3 kilograms. You can see the receiver here on the right. This receiver was probably about half a U and is a very sophisticated UHF receiver. It has multiple bands to interface with all the different radars. It was designed to be EMI immune so that spacecraft components would not interact with the receiver. Unfortunately, students did the impossible, and we did interact with that receiver. And it actually turned out to be a source of problems, and I'll talk about that later. But this is a beautiful receiver that SRI built, and generates 32 megabits per second, which over the course of a 5-minute experiment is 1.2 gigabytes per experiment. We wanted to run 1 experiment per day, and communication system is anywhere from 10 to 50 kilobits a second with a gigabyte of data per day. Link budgets don't work. Can't bring all that data down. So here's a picture of sort of the inner workings of a satellite and what was inside RACS. Our antenna system was tape measure material, and we joked around because the dimensions of this are published on the antennas, and we were trying to figure out if that was ITAR controlled. Interestingly, the width of the antenna is very useful. The wider that antenna is, the more broadband it is. So it allowed us to interface to more radars because of the width of the antenna. But this spacecraft is all electronics. We've got our antenna system up here that drives our antennas, payload receiver. We had a payload interface module, which is basically an FPGA that took all the data from here that we could then feed into our slower processors. We had a GPS receiver. We had a UHF radio. We had a lower speed S-band radio. We had a flight computer based on the MSP430, lithium-ion battery packs, a Michigan-built power system, an attitude determination board with magnetometers, gyros, sun sensors, and an instrument data processing unit, which is basically a Linux box, a Linux machine that would take the 1.2 gigabytes of data and compress it down, process it down, not just compression, but process it down to about a couple hundred kilobytes, and then our GPS antenna. This integration of this stack was probably one of the more challenging things that we had ever done. I mentioned Opal and how the batteries were packed in epoxy with a big aluminum box all around it. We don't have the mass or the space to do anything like that in the satellite. We have a super sensitive GPS or super sensitive payload receiver, which picks up every RF transmission from the ground as well as from the satellite. One of the challenges is that modern power systems are efficient because they switch. And they're switching at a particular frequency, and that frequency emits RF. We can tell you exactly, the receiver can diagnose exactly what's going on in that power system. We had a 50 megahertz clock on our FPGA that the harmonics put us right into our passbands for several of our receivers, receive frequencies for our payload receiver, and again, knocked out our receiver. So really, when you take the payload and you interact it with the rest of the bus, you find out all sorts of features of that bus system. And it takes quite a bit of work, depending on your instrument, to figure out how to get them to play well together. So RAX-1, we did an experiment, several experiments on RAX-1. This is the one that we downloaded. This is 5 minutes worth of data. We are looking at a delay. So this is a radar. How long does it take for the signal to be transmitted and then received by the spacecraft? You can see the main radar beam right here. These are the side lobes off this 2 megawatt transmitter that the spacecraft is picking up. This is all clutter and noise. Some of these might be echoes from meteorites, things like that. We were very excited about this because it mirrors what's going on with our main radar beam, and it looked like echo. So we dove into it, we dove into the details, and then we did some geometry work and some other investigations as to what's going on. And the US has a missile defense system with a transmitter right here. RAX flew across the main beam of that radar system, and our anomalies, our echoes, turned out to be somebody else's radar. So it's a fantastic way of, real data is fascinating, and being able to extract out, is this real noise? Is this spacecraft? Is it real signal? Is it spacecraft noise? Or is it somebody else injecting noise into you? Really opens up the doors for some very interesting challenges. So this experiment showed that RAX, the whole full system, end-to-end, was working great, but we didn't get the echoes that we were looking for. Unfortunately, RAX-1 had a power failure, so we had a fundamental flaw in our designs of our solar panels, and the spacecraft lasted for several months and then slowly dropped off in power production. So you can see on RAX-2, we reworked the panels. Unfortunately, we were able to get a very fast launch through NASA to launch the second spacecraft. We built it in about 6 months. And it is on orbit, fully functional. It's probably close to 260 days right now on orbit. But it was great to sort of rebuild this mission, still within the same funding cycle. We had a little bit, the whole mission was about $1 million. We had enough spare hardware, enough of the team still around that we could build this relatively cheaply and fly a second satellite. So we ran another experiment on RAX-2, and you can see this experiment here. Here's the main radar beam. We're doing some diagnostics on the ionosphere. So not only is the radar interacting with RAX, but it's also shooting its beam around to measure temperature of the ionosphere. You can see we're getting additional radar noise over here. And again, this shows that the system is working fully functional. You can see the magnetometer readings. Generally, we like when the magnetometers are very, very active. The time scale here is on the order of hours. You can see that timing is very important. RAX is flying through. We have to time the experiments at just the right time, or hope they show up at just the right time, because we can't really control our orbit, and we really can't control the sun and when it's interacting with the storms. So we're sort of at its mercy. But back in March, we had a great event. So in March 6th, there was a nice flare. There was a coronal mass ejection that sent some nice activity towards the Earth. There was a very impressive substorm that ensued with brilliant aurora, and you can see the magnetometers going crazy. Bucking broncos, I think, is the term that the magnetometer folks like to use. Riding crazy magnetos. And so our first mission, so we flew through these various events with the radar system fully active. We ran 3 experiments back to back. Each time we did an experiment, we checked the magnetometers on the ground to see how things were going. And on the 8th, the geometry worked out perfect, and we detected our first echo. So here you can see the faint echo coming off the main radar beam. this echo corresponds to exactly where we thought it would have been. And this is fantastic, fantastic data. The scientist, Hassan Bachavan, who proposed this idea, and when he first came out with the proposal, there's an expert in radars, and he said, it's impossible. There's no way they're going to be able to detect these things. And so we were like, we need to talk about that. So we actually ended up writing a paper with Mike Kelly. Hassan was doing most of the work. And they went back to first principles. They went back to the calculations and said, no, 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 no. We think that if they're there, there's enough signal strength to pick this up. And sure enough, there was. So if you zoom in at the echo, you can see this is the echo region. This red line is basically just an eyeballed fit of the general direction of this with respect to the delay. This black line shows the delay for irregularities that are at 100 kilometers. And you can see that we're picking up irregularities around the 100 kilometer range. Like every good scientist, he's got this processed summarized data, which is about a couple hundred kilobytes. Now he wants raw data from all this time period. 32 megabits per second over the course of several seconds adds up really, really quickly. So our first calculations on how much data he wanted said it would take like 4 months to bring this data down. So we've been working with him to actually extract out features of the radar data. The radar data has a pulse, and that pulse is very well timed, which means once you find one pulse, you can extract out all the other pulses without bringing down all the raw data. And so we've been doing that. So there's a student team, John Springman and Sarah Spengler are here, both leading that effort to bring down this data. This is some more analysis. You can see time again. You can see the peak in the signal to noise ratio of the radar signal that we're detecting. This peak corresponds to this spot, which is the perpendicularity. So this is a measure of the anomalies and how far off from the magnetic field they actually are. This peak corresponds to 90 degrees, which means they are very, very well aligned with the Earth's magnetic field. We can actually go in and view that alignment better than anyone has ever done in the past, which is fascinating. So we can zoom in again and see. We can take a look at the degree of alignment, and you can see it's confined. These anomalies are confined within plus or minus 1 degree from the Earth's magnetic field. Again, at polar geometries, this has never been measured before due to the way the geometry of the radar systems work. So this small CubeSat has fundamentally enabled new types of measurements. So we're doing the same thing again with the aspect angle, so trying to take a look at the various angle with respect to the 90 degrees. This is at 100 kilometers, 105 kilometers, 110 kilometers. So we can get a very good 3D view of this system and what's going on with these anomalies. So we did another experiment April 25th, and again, we detected more echoes. We are now in the process of downloading that raw data. Have we finished that yet, John? We're pretty close, right?
We've got all the April 25th one, yeah.
Okay. So we're also working on another experiment. So these were all over Poker Flat, Alaska. And we've been running with Resolute Bay in Canada. And again, you can see that echo. So there's a lot of echo. There's a lot of these field-aligned irregularities that RAX is picking up. And it's been a great proof of concept, a great initial assessment into the geometry and the fundamental physics of what's going on. So this is kind of a detailed chart. I won't get into the details of it. But this is the highest resolution that we've ever obtained for looking at these anomalies. This was a high-risk mission that was potentially infeasible from sort of a first principles perspective. The scientists went back, they studied it, they said, yes, we think we can do it, and now we've actually measured this anomaly. So this sets the stage for even full or more detailed assessment. This receiver system is extremely small. We can put it on another spacecraft, we can build additional free flyers. There are all sorts of places we can fly this payload system. But the work's not done. There's a lot of details. One of the interesting details is timing. So what time is it on board the spacecraft? What time are the signals being received and measured? And timing is fundamentally important to many of these scientific missions. And that's something that most tech demo missions just don't deal with. So being able to get microsecond, nanosecond time resolution into something that's this small is an extremely interesting challenge. So not only have we done science, but we've also been working on engineering results as well. So most people, when you do a magnetometer, you like to deploy the magnetometer outside your satellite because it's susceptible to internally generated noise. So we are using our magnetometers for attitude determination, which means our cleanliness requirements are much less strict, much easier than, say, a science grade magnetometer. But due to constraints, we buried our magnetometers inside the satellite. We had 2 3-axis systems and at least 4 dual-axis systems set around the outside of the spacecraft. We put the magnetometers right on top of our power system, and our power system uses inductors, and inductors generate magnetic fields. So when John, our attitude determination guy, saw this data, he just went crazy. And he's like, this is terrible data. And I said, no, this is an opportunity. Because there was a reason why we put a lot of magnetometers on the spacecraft. And the goal was to find this problem and to make it painfully obvious. So this is time. It's about an orbit's worth of data, 90 minutes. This is magnetic field strength. The black line is the predicted value based on the models of the Earth's magnetic field. The red line is what we're measuring on board the spacecraft. So you can see it follows the general trends, but it's terrible. So we did some more analysis, and one of the things that John noticed was that if you plot the sun indicator line, that when we're in the sun, we are far noisier than we are when we're in the dark. Okay, so this clearly indicates that whenever our panels are charging, our system is far noisier. And it actually points to not only the panels themselves, which are generating currents, but also the regulators themselves, so the input regulators that are taking solar panel and converting it into energy that our spacecraft can use. So we came up with a very nice technique that basically takes all of our distributed current sensors and correlates that to the sensor readings that we are measuring and basically knocks out all the current-induced noise that our satellite is seeing. So you can see the bad data over here in the lower right-hand corner, and you can see the cleaned up data. And this basically added a couple degrees better attitude determination with this software technique. This technique is also used to calibrate our magnetometers. So we built this big, large Helmholtz cage that we were going to generate magnetic fields to sort of calibrate our magnetometers. That's all gone. We dismantled that entire system because now we can do this on orbit with the same algorithm. So if you want to talk more details on that, John's got a poster where he dives into some of that work, I believe tomorrow. We can also do other very interesting things. So when I showed up at Michigan, there was a researcher that was working on radar systems in UHF. I'm like, I'm building a spacecraft that's doing a radar system at UHF. Would you like to work together? She's like, I'm not really interested. So I said, no, that's unfortunate because it'd be great to have a radar expert at Michigan. So we went off and did our thing. And one of the things that we've been doing is measuring received signal strength on our receivers. So on our spacecraft, we can measure just simply how much power are we getting in. So this is a map of the entire world, and we are plotting our RSSI values, received signal strength indicators, as a function of position. So you can see that there are clearly distinct areas of noise and quietness. So as you'd expect, over the oceans, it's fairly quiet. Eastern Asia is extremely noisy. A lot of activity on our command and control channel in Eastern Asia. In northern Russia, there is also activity. Europe tends to be a little bit noisier. I have no idea what's in the South Pacific, but you can probably imagine some things. You can also see these various streaks, and this is our spacecraft. So our spacecraft will occasionally turn on a system that generates noise. In this case, it's our 500 megahertz Linux processor that is spewing out noise, and we can actually see it in our command and control channel. So I got a call the other day, and it was from the same colleague at Michigan, who's no longer at Michigan. And she's like, hey, we would love to do P-band received signal strength monitoring. I'm like, P-band? What's P-band? She's like, oh, UHF. We would love to have global maps of UHF capability. I'm like, we've got the data right now. So even piecing together a spacecraft, data that wasn't there before, we can actually throw this up and now aid in their future mission design. So these spacecraft, as they're flying, are a wealth of information. There is an insane amount of data that we can extract and that we can mine out. And as the community matures, particularly maybe in the software level, we can start to distribute this data, and it can actually start to be connected. And these onesie and twosie spacecraft can actually start to coordinate with one another and signal each other when particular events are occurring. So just kind of want to give a quick overview of some of the data. Right now we are data constrained, and we will be for the next, I think we're probably going to be data constrained forever, because people always want more and more and more data. However, this sort of briefly talks about some of the trends that we're seeing with the RACS as we move into full-blown operations. RACS is one of the few missions that is fully operational from a science perspective and from an operations perspective. We task the spacecraft every day. It is constantly downloading. We've got this very rigorous schedule that we are working to optimize to bring down our data. So you can see the first weeks of data right here. These are number of beacons. So we're going from 0 beacons at initial start up to several hundred. And these jumps are when our colleagues download data for us from distributed ground stations. So we are interfacing with amateur radio operators, and they collect data for us. Some of them are retired, and it's their hobby to do this. So every morning we wake up and we talk to our ham radio operators and say, we're going to download data here, we're going to download data there, and they bring it all back for us. This is great because we now have been collecting data for months, and you can see various trends. This is hundreds of megabytes. We've downloaded 100 megabytes as of the end of May from a 10 kilobit per second link. So that's extremely nice. This takes a lot of work to task the spacecraft. We had a failure I'll talk about in a few minutes here. We had holidays, all right, so this is the winter holiday, Christmas, where we flatline because no one's commanding the spacecraft. We have thermal issues, so we slipped into a period of full sun, which means the spacecraft gets hot, and we have to be able to survive that very hot environment. So here's just operationally the phases. Initial acquisition is always difficult. There's a lot of launches that are going to be going into space station resupply launches, and you may get a month, a couple weeks, maybe a couple months. It often takes that long just to acquire the satellites and to lock onto it and get communication. So we're going to have to acquire much more quickly in the future. We did full initial checkout. Things were going great. And then in January, into December, we had a failure. So our SD card, our primary memory system on our flight computer failed. The card became unresponsive. It was consuming more current, and the response back from the card was unintelligible. So we spent a month working through this, uploading custom commands to try to diagnose what was going on with the SD card. And for all practical purposes, the SD card is dead. It is no longer responsive. It indicates a hardware failure, and that hardware failure is representative of what happens when radiation takes out a part due to latch up. We don't know exactly what the failure is, but that SD card is non-responsive. So we had to go through and we had to upload code, rework around the spacecraft failure, and get the mission back up and running. You can see that happens here. We slowly start to ramp up, and now we're in a regular schedule of running experiments and downloading data. There were some comments on software and how important that software is. If you go back and look at our code, it says, if flight computer SD card fails, insert code here to recover. So we've got the hardware on orbit. There's redundancy there. We ran out of time. So it turns out the programmer and I, we spent all of our time integrating the satellite and debugging some EMI issues that we couldn't finish all the code. So it was there. But RACS is back up and collecting all this data. Now what's interesting is we are just one of 8 additional NSF missions. So NSF has been able to fund additional programs. RACS is on orbit, DICE is on orbit. DICE is currently going through checkout. They deployed 2 1.5U spacecraft with deployable booms. They've been using a 1 megabit per second radio and a very large dish to pull down that data. But there are now 8 teams across the country building these satellites. 8 teams doing things that have never been done before with these small satellite platforms. And that's extremely, extremely impressive. If you want to, go look through the slides and you can pull up those details. I want to quickly comment on sort of the team dynamics. Some of my key team members from RACS have been hired and are here locally, so I thought I'd say a few things about them. It's important to have intergenerational students. So the past program I was at, we had all master students, and it's impossible. It's very, very difficult to build a program on just one generation of students. So being able to build sort of a vertical system. I've got a kid whose father wants to come in and help out. Being able to postdocs all the way down to freshmen is important for this continuity in bringing things together. At one point, one of our key partners, Andy Kalash, was in Japan. So we pretty much had 24/7 work going on where we'd be communicating back and forth. Now, I wanted to talk about the team just briefly, so I have some quotes from various students, okay? So Matt Bennett is one of the best engineers you'll ever meet, and this is a quote from him. "The manual is in my brain. What's wrong with this picture?" That's an incredibly fast motorcycle, okay? Here's Matt Bennett. He's got a helmet on. What's he doing? He's jumping out of planes, all right? So this is the kind of energy, this is the kind of passion that these students bring to the project. And then it's a trick to a trick, an art, not quite a science yet, but how to bring a team together to enable this type of innovation and keep it going when things really are locked in people's heads. We just don't have the time or the money to fully document in traditional ways. Another thing, so this is a student, and he came to me and he said, "Why don't you like me?" And I said, "You don't do anything." And he said, "Well, what do you want me to do?" And that opened up a lot of doors in my mind. He went off and he helped design the power system. So here's our power system. We bought a commercial off-the-shelf system for like $30,000. It failed miserably. So we had to go off and redesign our own. So Kiko built this battery system, and that battery system is now flying on 2 spacecraft. Its Heritage is flying on a 3rd spacecraft, and it's performing flawlessly. All right. He then took his knowledge, he went to SpaceX, and the battery systems that flew Dragon to space station were his batteries. Okay? So this student said, "What's wrong?" And I said, "You don't do anything." So he said, "What do you want me to do?" So it's that idea of getting hands dirty, of actually building that was mentioned earlier, that's fundamentally important. He also taught me that when you look at a team, people have different strengths, and you got to find those strengths and pull them out. He's very good at talking. And he's helped me out of a few jams because he can talk. This is another guy that's at JPL. So he's fortunately coming back to Michigan, I hope, in the fall, assuming the weather doesn't keep him here. But can anybody read his shirt? Come on, someone's got to be able to read this.
If you got a problem, I'll solve it.
Excellent. Can you sing it? No? Okay, so it's an Ice Ice Baby. If you have a problem, I'll solve it. All right? So this kid, Ben, was amazing. So we went to a classic aerospace laboratory. So across the street from us is the Space Physics Research Lab. And I said, "Hey, look, I've got 32 megabits coming out of this system. All my students are aero students. They don't know a thing about electronics. I need your help to build this power system, and I can take care of the rest, or this interface system." They said, "All right, give us $100,000. Come back to me in 6 months, and we'll give you the hardware." I said, "No. We've got 3 months. I'll give you $50,000, and I want your engineer in my lab." They said, "We're not going to do it." So I went to my colleagues and in the W department, and they said, "If Ben can't build it, nobody can." So this student, this kid, this brilliant engineer designed this system with the advice of these squirrel engineers. So we took this student, we consulted with the professionals, but he would come back and they'd say, "Oh, it's going to take us 3 weeks to figure that out." He would do it that night. Come back and say, "We can't do it. We've got to do something else." So we've tapped into that kind of expertise and that kind of passion. By the way, Eric, if you ever meet Eric, do not let him touch your computer. He was one of the teams that broke into the DC voting system that they put online and said, "Please attack." And so him and his advisor broke in, they attacked it, secured it all up. It's a great, great story. He'd be sitting in the lab, he's like, "Hey, watch this." And next thing you know, Nick's computer would just start freaking out because Eric had touched it. But he programmed all of our Linux machine, and he did all the programming that's running and processing our spacecraft data. So these students are great. At the heart of every mission is a crazy scientist. This is Hassan Bachavan. You've got to have this crazy idea, and that's what excites me about seeing the astronomy stuff, is because you are trying to do things new that are breaking these molds. And so we need the engineers and the scientists to come together and say, "All right, let's try something brand new." We partner with global hams around the community. So John and Sarah have been working at optimizing these global hams. We get our daily emails from Australia. Actually, I didn't wake up to an Australian email today. Uh-oh, okay. But these hams are brilliant. These guys are incredibly, incredibly smart. We've got colleagues in Japan, North Carolina, Australia, and Germany. And these are the best RF people I have ever met. And they come in and they diagnose the problems. It's part of their hobby, and we all learn from them. And sometimes we were able to teach them a few things too. So there are many lessons I could dive into. We heard some great ones earlier on. One of the things is that failure is a fact, so deal with it. We like to build systems that don't fail, but honestly, they do. And you need to be able to recover from that and move on. So every spacecraft I've ever been involved in, even watched, has had some sort of failure. Your team has to be able to recover from that. The RAC's SD card failure, we knew how to fix it, we just ran out of time. All right, but we have to be prepared for those failures to deal with it. So there were some discussions on committees. We describe those as, we run our missions with 2 to 3 benevolent dictators. All right, not 1, not 6, but 2 to 3. These dictators drive the design, they control the design, and they're helpful. We like to run 2 or 3 because at any given time, we may be completely knocked out. I may be giving a test, my student may not have slept, so there's 2 or 3 that are working together. You need a sustainable pipeline. So the trick is how to figure out how to keep these things going. If you build 1, that's great. How do you build 3 or 4? We've got 3 in the pipeline right now that we're building, and it's a lot easier to build 3 than just 1. An open question that I'll leave for you guys to debate. Do you want your scientists and engineers together or on opposite coasts? There are pros and cons to both. Finally, I think these university class missions are important. Being able to have students involved when you're trying to do something that's completely brand new, that's never been done before, you have to have that innovation. They've got nothing to risk. They've got nothing to lose. They're willing to try anything. If you talk to big, large primes, they've got their reputation to lose. You have to have that university involvement because there's that creativity. We're showing with the NSF missions, with JPL and ESTO missions now, that we can actually demonstrate novel new things. There are significant constraints that you have to be prepared for. And in many ways, I think this is a new beginning. If you take a look at even something like Cygnus, all right, so you guys familiar with the Cygnus mission that's just been recently announced? It's a Earth Venture class. It's a $150 million mission to build small satellites. Michigan is the science PI, but we're not doing any of the engineering behind it. If you ever get a chance to dive into the details of the structure, you'll find buried in the Cygnus spacecraft a box that's 10 by 10 by 30 centimeters that has all the avionics, all the flight computers, and all the power systems. All right, so we've infiltrated that. At some point, those CubeSats will potentially be doing better new things, crazy things, and I think it's a new beginning. So thanks for your time. I appreciate it.